With only a few walls between an astronaut and a rapid death, what do we know about the various risks to the human body posed by space travel? Mark Shellhammer at Johns Hopkins Medical School has spent many years documenting and studying the threats.
Let's start near the top of the list and let's go down the top, maybe three or four. Radiation in deep space, meaning outside of Earth's orbit, is a lot harsher than it is in low Earth orbit. We don't yet have a good idea of just how bad that's going to be. Almost certainly, it would increase the probability of getting cancer over an astronaut's lifetime. So, okay, you could say that that's not a space problem, that's a terrestrial medicine problem, and cancers, many of them can be treated or even cured. The real problem is if there's something intense like a solar flare, then the radiation effects can be very quick and very dramatic. So, radiation poisoning, basically, and fatalities. Another one that people maybe don't think about as much because they think about the physiology. The other one is what is called BHP, behavioral health and performance, by which is meant psychology. The idea of getting a small number of people, putting them into a small space for 3 years, and you can't get in or out. Astronauts are very highly trained people. They know how to deal with other people. They know how to relieve stress, but still they're people, and this can be very stressful. Let me say one of the many physiological issues, which has to do with shifting of fluids in the body. So, right here, sitting in front of my computer during this interview, I'm subject to a gravity field, which tends to draw fluids downward to the lower part of my body. And of course, my heart pumps to keep the blood to my brain. When you go into space, that distribution of fluids changes. The heart doesn't have to pump so hard because the fluid redistributes itself. It's like going to bed and laying in bed. So the fluid will redistribute itself, including going up into the upper body and into the head. And that is, the jury is still out on the details, but we think that that is contributing to some problems that we've seen with changes in vision in some astronauts after being in space for a long time, possibly actual changes in the structure of the brain, which have been minor and reversible, so they go away when people come back to Earth. But we don't know if those are going to be continuing and getting worse when people are in space for a longer period of time, like a Mars mission. That's a very significant potential problem.
What can we do about these? Are these surmountable problems, or are we just going to have to confine ourselves and say long missions are off and we're just going to go for orbital missions and we will send robots and human avatars to do the faraway stuff?
We don't know for sure because there is no way to reproduce all of the aspects of a Mars mission except for actually doing a Mars mission. The research these days is heavily oriented to what we call countermeasures, which are ways to mitigate, alleviate these issues. I think none of them, I think, are absolute showstoppers. They will just make life challenging and interesting for astronauts. Two things that we know are successful: diet and exercise. Those are the two big countermeasures that are used on the International Space Station. If you eat right, you have to do things like replace lost calcium and things like that in space, and exercise. Those are pretty good countermeasures for a lot of problems. They don't address the radiation problem, the psychological problems, the other things. So for those, we don't yet know what the good countermeasures will be.
Have there been, as a result of this, when you stress the system in this way, learnings that we can apply here on Earth? Because a lot of people, when you ask them about humans doing exquisitely unusual things or extreme things, like going to the top of Everest, they say, well, actually, we now know a lot about how the human body deals with very low oxygen conditions in intensive care because people went to the top of Everest and took blood, for example. So are we using being in orbit as an aggressive learning opportunity to improve lives back on the Earth's surface?
Absolutely. One of the examples is in my particular field, the vestibular system. there's a vestibular system, a balance system in both sides of the head. And they work together just fine, but there's reason to believe that they're not exactly the same, that there might be small differences in the anatomy or physiology on the right side, the left side. You don't see that typically until you change the gravity level. So we see aspects of this, manifestations of this asymmetry when people go into space. It turns out to be very interesting. Does it have potential consequences? Is it a form of a pathology that we don't typically see on Earth because it's masked by the normal 1G of Earth? That's quite possible. We've talked about some of the impacts on the human body, and we've talked about hazards. A defining feature of spaceflight, which is to me as a researcher, what makes it absolutely exciting, is that exposure to multiple simultaneous interacting stressors in space and the body's response to them is going on all at the same time. So you have a lot of different body systems all undergoing changes all together at the same time and interacting with each other. That's a situation that we don't typically study on Earth. Typically, we parse out the body and study one system at a time. But if you have somebody with a complex disease or aging, there's a lot of different body systems undergoing changes at the same time. So if you want my opinion about what's going to potentially be the biggest scientific return from sending humans into space, it will be getting a handle on that body response to multiple simultaneous stressors.